Hello and welcome to R&D Mathematics. Today we are going to talk about the end behavior. End behavior of higher degree polynomials. Now we have been talking about higher degree polynomials and we talked about zeros last time and some other stuff before last time, and today finally the end behavior, and then we are in a position to draw the polynomials. Now let's have a look at that. Now let's say end behavior means as x gets larger or very smaller, as x goes to infinity or as x goes to negative infinity. That is what's known as end behavior. So in other words, when you have your graph, what will happen when your x is large in that side and that side? Now this is really easy, guys. This is you know what, let me write down f of x equal, let's say a n x to the n plus a sub n minus 1 x to the n minus 1 plus a1x plus a naught. So this is a nth degree polynomial. Now the thing that you have to understand, this has same behavior as the power function. Remember, we learned about power function in the beginning of higher degree polynomials. As the power function a(n)(xn) as x is large. This is all you need to know. Now, in simple words, this means, for example, the function, the fifth degree polynomial, let's say 3x to the 5 plus 2x to the 4th plus 5x squared plus x minus 1 behaves like this guy right here for sufficiently large for large x. Let me just write for large x. This means, see, remember we learned how to find zeros and all the multiplicities of zeros, what will happen, all those things, y-intercept, x-intercept. So, and I'm not going to do that here. Assuming, let's say, you have all those things like that, and when x is going to infinity, what is going to behave? So that behavior is same as the first term, the highest power term. The reason is, now let me explain the reason over here, erasing, without going to a new slide. The reason is very simple, because, say for example, if you take f of 10,000 or f of, let's say f of 100,000, this guy, see 1, 2, 3, 4, 5 zeros. So in other words, f of 10 to the 5th. When I plug this in my function, what's going to happen? 3 to the x fifth, but x itself is 10 to the fifth, so it raised to 5th power, and then you have 2 to the x fourth, so 10 to the 5th, like that. But this term is much larger than all these terms, because the powers are increasing. If you think about it, this term has 10 to the 25th power, and compared to this term, yes, this is big, 10 to the 20, but it's compared with this is large. So when x is getting larger and larger and larger, this polynomial right here is dominated by, or it's getting closer and closer to its highest degree part. Now, in other words, let me give you another example. Let's say you have a function like f of x, 10x to the 7 plus x squared minus x minus 7. Now, after we find our zeros and all those things, all those zeros, you don't know somehow. And to complete the graph, you just need to know what it looks like. This first term, not the first term, I mean the highest degree term. So it is dominated because if you put a large number like 100,000 or million, this term, the actual function and the power function are very similar because of the highest degree term, that is known as the end behavior. Now, let me quickly recall you what you need here. Actually, I drew a table few 3 4 maybe videos ago. Let me quickly draw that table again. So the power function AXN, remember we did this, it can be, n can be even or odd. But why we have 4 columns? Because n can be even and a can be positive and negative. And here also n can be odd and a can be positive and negative. And in that video we learned, I'm not going to explain everything here, I'm just recalling you, so this goes hand to hand with that video. So if n is even and a is positive, you will always get a shape like this. So this is the end behavior, this is what you need to remember. And you know what actually you need to remember is this part. It's going to infinity from positive infinity, and when x goes to infinity, your function value is going to infinity, and when x goes to negative infinity, it still goes to negative infinity. And even negative, that's going to happen when x goes to infinity. See a shape like this, but the part you need to remember is this. For example, you will understand this crystal clear when we do more examples in our next video. So n behavior is like this. So here the first one, x goes to infinity, fx goes to infinity. X goes to negative infinity, fx also goes to infinity, because here see it's rising. And here x goes to infinity and x goes to negative infinity. In both cases, fx goes to negative infinity. But the odd case, I think here mistake, odd. And the odd case we had like this, and the other way around like this. So in that case, when x goes to infinity, function f of x goes to infinity, and x goes to negative infinity, f of x goes to negative infinity. And here the other way around, when x goes to infinity, function is decreasing, it's going to negative infinity, and when x goes to negative infinity, function is going to infinity. Now what you need to remember, this idea again. Yeah, the basic shapes, if you can remember, that's good, but this is the only thing that will be. For example, guys, let me give you an example over here. You know what, let's say you have a function, some power function, 3x to the 5th plus 4x squared minus 7x plus 8, some kind of power function. And then let's say you have actually found all zeros and done everything. You just have to, let's assume, right? Let's assume we have completed all the work and we know some zeros, and our function looks like this. And then to complete it, looking at this, we know x to the 5th and 3, so positive, odd positive. So going back previous, odd positive this way, so it looks like, see, it looks like this. So what you need to do, complete it like this, simple as that. So this is what is known as end behavior. Now what we are going to do, in our next video, we are going to put everything together and draw graphs of functions like this. Okay, guys, thank you.